The way of choosing a pivot element in Gaussian elimination is taking the absolute value of the most dominant coefficient. Check how complete pivoting solves a system of equations here in numerical solutions to see problems. Gaussian elimination is one approach in solving systems of linear equations. This method uses half of the solution by creating a triangular matrix, then computing for the values by algebra. In transforming a matrix, extract the coefficient of each term and arrange them in an augmented matrix. The three variations of Gaussian elimination are without pivoting, which takes the elements and the arrangement of equations as they are. Next is partial pivoting, which allows swapping of rows in order to arrange elements to pivot, that is, the elements used to zero out other non-significant elements. The third is complete or full pivoting. This approach allows the interchange of both rows and columns to have the pivot element. Gaussian elimination with complete pivoting is the most stable approach. This is done by considering all the elements when choosing the pivot. The rearrangement of the elements can be done by interchanging rows and columns, which makes this type very versatile. However, although this method is the most efficient, be extra careful in tracing the arrangement of the variables. Just like the previous examples, this is the second example for Gaussian elimination without pivoting, and also with partial pivoting. We recompute it using complete pivoting this time. The preliminary step in pivoting is to choose the pivot element, where, for full pivoting, we are to choose from the 16 elements. The highest value is found as 4 at row 4, column 2. So we need to place this as the first element of row 1. The first operation is to flip rows 4 and 1, thus placing 4 up the second column. Since we had a row operation, the designation of each column remains the same as X, Y, Z, and W. Then flip columns 1 and 2, which then finally placed 4 to where we want it to be. Also with the interchanging columns, the variables are now arranged as Y, then X, with Z and W. The next step in creating a pivot element is to make it equal to 1. So the first row is then divided by 4. Fix the matrix by recomputing the elements, starting with 4 over 4, which is 1. Then 1 over 4 is 0.25. Next is negative 2 upon 4, giving negative 0.5, followed by 1 over 4, which is 0.25. Then last is 0 over 4, which is still 0. The pivot element is then used to zero out the elements below the pivot row. So, for the second row, we zero out negative 1, and that is by using the operation row 2 plus row 1, where the first element then becomes negative 1 plus 1, giving 0. The next is 2 plus 0.25, making 2.25. Then 3 plus negative 0.5, resulting to 2.5, followed by 2 plus 0.25, which is 2.25. Then the last element is 20 plus 0, which is still 20. For the third row, zero out 2 using the operation R3 less twice of R1. The updated third row starts with 2 minus twice of 1, which makes the first element 0. This is followed by 3 less twice of 0.25, giving 2.5. then 1 minus twice of negative 0.5, giving 2. Then negative 1 less twice of 0.25, resulting to negative 1.5. The last element is 5 minus twice of 0, also yielding 5. Moving on to the fourth row, where we can zero out the first element by R4 minus R1. This then starts with 1 minus 1, which is 0. Next is 1 less 0.25, which becomes 0.75. Then 1 minus negative 0.5, yielding 1.5. And 1 minus 0.25 is another 0.75. The last is 10 minus 0, which is still 10. After cleaning the first column, move to the second and start by identifying the pivot element among the 9 remaining elements. The highest value is 2.5, found on columns 2 and 3. If we choose to use 2.5 from the third row, we swap the row to the second, after which we divide the pivot row by 2.5 to create 1. The first element is 0 over 2.5, which is still 0. Next is 2.5 over 2.5, giving 1. The third is 2 upon 2.5, which is 0.8, followed by negative 1.5 over 2.5, resulting to negative 0.6. The last is 5 over 2.5, and that is 2. With the pivot row already fixed, zero out the non-significant elements in column 2, starting from row 3. We use the operation R3 less 2.25 R2. The first element is 0 minus 2.25 of 0, which is 0. Then 2.25 less 2.25 of 1 is also 0. The third is 2.5 minus 2.25 of 0.8, which gives 0.7. Followed by the fourth, which has 2.25 less 2.25 times negative 0.6, giving 3.6. The final element in the row has 20 minus 2.25 times 2, which leaves 15.5. Do the same elimination to the fourth row with the operation R4 less 0.75 of R2. This starts with 0 less 0.75 of 0, which is still 0. Next is 0.75 less 0.75 times 1, which is also 0. The third is 1.5 minus 3/4 of 0.8, resulting to 0.9. The fourth element is 0.75 less 0.75 of negative 0.6, which becomes 1.2. Then, 10 minus 0.75 times 2 gives 8.5. The second column is already complete. Move to the third column and start with the determination of the pivot element from the 4 remaining elements. The highest value is 3.6 from column 4. So we have to swap columns 3 and 4 to position 3.6. The interchange of columns also rearrange the designated variables into y, x, w, then z. Next is to create a pivot element equal to 1, and that is by dividing the third row by 3.6. So the elements start with 0 over 3.6, which is 0. And this is also true for the second element. The third is 3.6 over 3.6, which is 1. The fourth is 0.7 over 3.6, giving 0.1944. Then 15.5 over 3.6 is 4.3056. Zero out the remaining element below the diagonal of the triangular matrix using R4 less 1.2 of R3. The elements of the fourth row change starting from 0 less 1.2 of 0, which is 0. The two succeeding elements also yield 0, that is from elements 2 and 3. The next is 0.9 less 1.2 of 0.1944, simplified as 0.6667. Then last is 8.5 minus 1.2 times 4.3056, reduced to 3 and 1/3. After having a triangular matrix, use back substitution to come up with the variables. Take note that the matrix now starts with y, followed by x, then w, and z. From the bottom row, 2/3 of z is 3 and 1/3, where z is 4.9997, or simply 5. Move a step above and find w plus 0.1944z as equated to 4.3056. Plug 5 for z and transpose terms to the other end to have w as equal to 4.3056 less 0.1944 times 5. Simplify the equation and get w as 3.3336. For the second row, there is x less 0.6w plus 0.8z as equal to 2. Place 5 for z and 3.3336 for w, and then place the terms with the constant and have x as equal to 2 plus 0.6 of 3.3336 less 0.8 of 5. X is then computed as 0. From the top row, the equation is y plus 0.25x plus a quarter of w with half of z as equal to 0. Place x of 0, w of 3 and 1/3, then z of 5. Transpose the terms to the other side and simplify to have y as equal to 1 and 2/3.